any point of time, because the idea of this thing is not like a lecture. We would like it to be more interactive over the next 5 days, okay? So first thing is, okay, so wanted to give you an introduction, and I already said during the previous meeting, previous presentation, previous discussion, that where we are, what's the scale of it. So if you see the energy related CO2 emission, this is actually increased by 1.1%. This, you are seeing this, all the numbers I'm giving for 2023, because 2024 numbers are yet to be confirmed. So like a lot of these numbers are coming up. So we'll be getting those things, numbers correctly, but 2023 numbers are all confirmed. So this actually increased by 410 million ton, and this is the new record in 2023 that which we had. And if you look into it, in 2022, the increase was about 490 million ton. So it's not that much different in 2022 versus 2023. And the other thing is that if you look into the coal, it actually contributed to the 65% increase. So this is one of the big things, that who is the main contributor, so we identify that. The other thing is that if you look into that, how much of these is basically coming from burning of fossil fuels, you can see that out of this 37.4, about 34 billion ton is coming from burning the fossil fuel. The rest of the CO2 is actually coming from a lot of other sources, like for example, chemical production. If you see in the lot of the petroleum and the petrochemical processes where the CO2 is getting produced, and those are getting emitted into the sources. There are other sources also that is also produces CO2, including a lot of animals and other sources too. So those are not really much. Most of it is coming from burning the fossil fuel. If you notice here that 45% of that is coming from the coal, 35% from oil, and 20% from gas. Once again, it says that majority of that is coming from coal. Now, if we compare this with respect to how the advanced economy is actually doing, like these are mainly the G7 countries, their GDP grew by 1.7%, but emissions fell 4.5%. And this is a record decline. There are actually a lot of incentives, as I will discuss. Many governments actually came up with a lot of incentives. Like as we are discussing today, government of India is coming up with a lot of incentives as well. So because of all of those, there is a lot of declining in the emissions coming. So for these countries, this has decreased by 520 million ton, and this is now back to their level 50 years back. So this is really a great news. So that tells you it is possible. It's not a problem that we cannot solve. It requires a lot of government incentives and the works and the focused work, but with that it is possible for us to go there. If you look into it, like as I said, the coal was actually one of the main contributors. So now if you look into some of these countries here, their coal demand is actually at the 1900th level. So that basically means that it's very low right now, and that's one of the main contributors there. Now, if we look into some of the Asian countries, now the statistics is not available for all countries. So I know that this organization, IEA, is one of the organizations. So look into this link here. It will keep updating every year so that you get the numbers, because I wanted to, they actually track the CO2 emission all over the world. It's not necessarily very well documented for all countries, but some of the countries it is well documented. So it's observed that the China actually went up by 565 million ton in 2023. This is by far the largest increase globally. Also, the per capita emissions in China are now 15% higher than any advanced economies. In India, the emissions during 2023 went up by 190 million ton. And it also said that there was a weak monsoon, increased demand for electricity, and that also cut the hydro production. So those are the contributors for the CO2 emission here. But I would say the per capita emission in India is still remain very low compared to the global averages that are. So that's because of our lot of populations and lack of energy demand that our emissions still remains low. But a lot of the emissions in India is because of the coal, and that is something that I'm sure that is being looking into there. Now, what is happening in terms of the CCUS? There are about 45 commercial entities that are operating all over the world. When I say commercial entities, these are not pilot plant. This means that these are commercial plants which are capturing CO2, and they are either utilizing the CO2 or they are storing it, right, underground storage. So it is basically all of those. There are 45 of them there. And these facilities captures about 50 million tons CO2 annually. This is a big one, but I wanted to give you some examples of some of these projects here. This place got cut down, but I'll read it for you here. So a couple of example plants like what they are doing right now. So let's focus on that. So this one, the Blue Flint ethanol project. This is actually storing about 600 metric tons of CO2 per day, underground about 1 mile below the surface in one of the formations in North Dakota, USA. So this is basically the ethanol production. As you know, that there is a lot of, from the fermentation process, it produces CO2. So they are capturing the CO2 and they are putting it under the ground. And North Dakota has a pipeline for CO2 for quite some time. They have already pumped about many million metric tons underground. They are monitoring all of those capture plants there on a regular basis. This is another one these are all that actually started in 2023. So these are some of the plants, but I'm not talking about the other ones. These are the ones that started operating in 2023. The Lindy Clear Lake Capture Facility, this is in Texas there. And what they do is that they supply CO2 and hydrogen to a Celanese plant that is converting that to producing methanol, actually. So Celanese, as you probably know, that they are one of the companies who are working in the green methanol production. So this is also another usage that people are using. Heirloom and the Global Thermostat, they have now 1,000 tons CO2 per year DAC facility, and in the United States. And then there are also 4 projects in China that actually started here. In the Petronova plant that has actually operating for quite some time, but it got shut down because of other maintenance and other work that they had to do here. These guys are actually capturing about 1.4 million ton of CO2 per year. This is outside of Texas also. They are using it for enhanced oil recovery. So this sends it about 130 kilometers there. And as you will see that for my discussion, other thing which I'll keep discussing about the CO2 transport, which is one of the very critical aspects that we need to consider, CO2 transport. So what it basically tells that this is possible and this is happening in many parts of the world there. Any questions so far from any of you? This is mainly statistics. I put all the websites here, and these numbers keep updating and all that stuff. So you can look into that going forward. Now, where we are, like you all know about the Paris Agreement, right? We are really behind. Many countries committed, but there is not steel on the ground. The point is that the commitment does not help unless you put the steel on the ground and do something about it, okay? That's a lot of things trailing down. Now, currently, this is the good news is there are about 700 projects in various stages all over the world that are actually trying to capture CO2 or trying to utilize the CO2. One of the big things that is coming here is that in terms of the value proposition. The problem is with the CO2 is that you capture CO2. There is no issue in terms of capturing CO2 and putting it underground. That can be done. No issue there actually. The problem is, as you were saying, it's one of the cost. Second is, what is the value proposition? Like, how do you get the money back, right? Now, that's why a lot of work going on in terms of the CO2 utilization, in terms of, as I was showing, that enhanced oil recovery. Like one of the earliest plant you probably know is actually in Canada in the Boundary Dam. And I have visited that plant actually, where it's about 400 megawatt power plant. They capture CO2 and put it for the Canadian oil sand recovery, right? And those guys are actually monitoring those spaces for many years. And sometimes actually this can be seen through the propagation of the seismic wave. So on the other side of Canada, that place is actually Japan. So they're actually from that side, from the earthquake, they actually monitor that if there is any CO2 getting penetrated through the ground and going other side. In fact, actually, if you have a seismic wave, if you have a CO2, that actually let you propagate it. So Japanese researchers, they were actually always monitoring that site where they are actually storing CO2. But those places actually very securely storing CO2 for many, many, many years now, actually. So it is possible, it is happening, but we have to think about some value proposition here that everybody is trying to work towards. The other thing I would like to say here is that there is about 35% increase in the announced capture capacity to be realized by 2023, and the storage capacity is 70%. A lot of places where the storage is being taking place, I am not really sure about India, and I'm sure many of you may actually inform me and are well aware of it. But in the United States, I know that for the entire country, they have a map now where the CO2 can be located. All the natural formation in the countries has been mapped. Every state, every locations that where you can securely store CO2 there. So if there is a local capture, you can store under the ground, and those are secured. Of course, there is monitoring and other things, but this has been mapped by the geological survey groups actually. So that's why there are announced storage capacity rose by 70% here, and that is what I said, that by 2030, that should be captured when will go up by 435 million ton per year, and then 615 million ton CO2 for storage. This will go up there. However, these are positive, but we are still about 40% and 60% with respect to the captured and stored with respect to net zero emission level. Based on also all these propositions and based on what is expected in terms of the renewable penetration. As a researcher, and I see all your diverse background, the other thing you have to keep in mind is that when you actually try to do all of these and think about bringing the renewables, when you start going beyond 50%, it can be a troublemaker. The problem, as I was saying, that if you have a wind energy and wind suddenly falls, and as they always claim that whenever you needed it, you don't get it. Right? That's the problem. You have a wind, you have the solar. On a summer day, you need, I need energy because everybody is cranking up their AC, but that's the time you will not get it. What do you do at that time, right? So if you are shutting down these plants and you go to renewables, you have to have a backup plan what you do with it. So bringing in 100% renewable is not the solution. What do you do during the night time? Can you store that much of energy? Let's see what we see here as per their IEA projection. So by 2030, this is the gap, and then notice this part here. This is basically a lot of these things we are expecting to really be, how much of these will be operating, what is under construction, what is under advanced development and concept and feasibility, right? So if you notice this part, this is not really increasing by that much. And as you always fondly say, there is something called a valley of death, right? They always say that there is about only 5 to 10% of the project can cross the valley of death. So you get the project, wonderful, wonderful, wonderful. At one point of time, your business proposition goes down, you make loss, 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 or some other problem shows up which you do not anticipate in the lab scale. When you start doing piloting it, you start realizing this issue is commercialization, and that gets value of death. This number I said, this number is kind of from US Department of Energy. They basically say generally their experience is it's only 5 to 10% of the project will cross the valley of death. Okay, so lot of projects we need so that we can have a large number of projects that can cross the valley of death. This is the reality because we don't anticipate from lab scale analysis what will be the problem. So I'll be switching gear after this, but let me know as of now anybody has any question, any perspective or any thought, please. Yes.
It's a question plus perspective. So as of now, the slides that we have shown, sir, most of the carbon capture that is happening is mainly for the oil industry in terms of enhanced oil. So just trying to understand from the global perspective, especially for the Western countries, means what's the plan for the conversion? Means until and unless the conversion technology is well developed and commercially applicable, the commercial numbers will not match. All this enhanced oil recovery, it was mainly done by the oil companies. Occidental, Nova Petra is there. So to have a large scale implementation in hard to abate sector segments, so it's very much important to have that utilization factor coming. Utilization factor not only for the enhanced oil recovery, for say it might be permanent storage of CO2 in form of say building material or maybe synthetic
Right.
oil and so, or maybe other products replacing the existing say fossil fuel based petroleum with this kind of a net zero kind of a petroleum. So just trying to understand how it's been going. And another perspective is this, in terms of government of India, actually government of India has come up with a policy, though that policy is currently in the draft stage. Bureau Energy Efficiency has come up, carbon capture trading scheme that will be implemented from 2026. Unfortunately, means as a commercial person, I do feel that carbon capture is not included in that. But in that, government has included green hydrogen production from biomass or bio-CNG. Another, there is a clause called alternate fuel. So based on Indian scenario, we might use in that way so that there will be commercial value for carbon capture and utilization.
Yeah, very good. Thanks for that comment. So those who are online, I'm not sure you could hear or everything. They could. Okay, so those who are online, the question was that what about the CO2 is being used right now mainly for enhanced oil recovery. So what about other usage of CO2, the CO2 utilizations? And there was some perspective about some of the government of India policy in terms of mainly focusing on the green hydrogen, but not necessarily for the CO2. What I would like to say here is that because the massive amount of CO2 that is getting generated, you think about CO2 utilization, any market, carbon market that you think about right now, it will be saturated. So if you think about urea production, you think about methanol or ethanol production, carbonate productions, or there are a bunch of other chemicals, thinking about the formic acid and others, any of those markets based on their current demand, they will be saturated. So the idea here is that some of those can be going to the value addition, but some of them actually has to be stored only under geological sequestration, which is not adding value, but it is mainly for the storage purposes. Like what I was saying was about that methanol production plant, and they are getting it from fermentation process, but that entire CO2 is getting underground. So they are storing it. So they are making money by selling ethanol there, but this is coming from there. The other thing which I will be discussing in a moment, that this comes from another perspective. So the question is, can the storage of CO2, can I make money by storing CO2? Yes, you can. I'll come to that in a moment. Yeah, so I know that green hydrogen production does not come on its own. there is a CO2 footprint. So you have to do the life cycle analysis really to understand that what is the CO2 footprint of that. So the issue is this massive amount of the CO2. Can I have the demand of carbon products equivalent to the 34 billion ton CO2 equivalent? No, we don't. Any market you think you will saturate it. So this goes to my next thing here is that you can, this was a very timely question, because my main thing is that what the government can do as part of an incentive to make this capture possible. So one thing that was done in the 2022, the Inflation Reduction Act, they did this 45Q tax credit, which gives you $60 per ton of CO2 used. So if you have 60, that basically means that if you're able to capture CO2, say, by $40 per ton or $30 per ton, then this can actually, you can make money by doing this. But now you say, well, my technology will take you $200 per ton. You cannot. So this is a competitive market, definitely, but this is a government incentive. And a lot of those projects that I was saying in 2023, they were actually making money because of this, because the government said this incentive. So that's one thing. The other thing that was done was this, the clean fuels and product short, which is basically like producing fuels and chemicals that through CO2 utilization, that also give you that much incentive there. Like for example, if you're producing ethanol there, but you are getting the CO2 released to the environment versus you say, this CO2 I'm utilizing somewhere, or the CO2 is being captured from another plant and I'm converting this to a fuel, you get these as a clean fuels and products incentive. So this is all depends on the lot of government support that will be needed, at least for now, to make these projects off the ground. The other thing is that European unions also came up with a lot of these incentive. One of these is this refuel EU aviation proposal, and that actually synthetic fuel for aviation, that was really targeting about that. Many of you know about the SAF incentive all over the world that is going there, and then how much to be increased slowly. Then Canada also, they had a lot of proposition there and how much they will be funding. So one thing which I would like to say is that as of today, you go to somebody and say, do the calculation for me, do the economics for me, and somebody will say, hey, yeah, you know, your technology will cost you $100 per ton. This is not the calculation for nth of a kind. You are doing the calculation the first of a kind. That basically means is you are saying, this is my first plant I'm building. But remember, like when these plants are built, like thousands of those, and you are doing the mass scale production of the adsorbents, solvents, or other technologies, the cost will actually go down. You have to go there. Like Ajay was saying, the renewable energy, that big penetration that you see right now in the United States, lot of those was because of the incentive that was taken during the Obama administration there, when they actually, the government actually gave lot of discounts. So I'll say, okay, I'll give you 50% discount, you buy solar. So what it actually helped is that a lot of people actually started buying it. Like in my household, I can put a solar and I can sell it to the grid. I can make money actually. But I cannot make money in the first year, second year, because I have to make massive capital investment. But if the government come and says, I will give you 50% for this one, so do not worry, then also take tax credit. So I'll give you tax exemption and all of that. Then once I buy it, then my capital expense is done. Then I am contributing to the market. So a lot of roles and incentives from the governments are actually needed for reducing the cost. It's almost like a chicken and egg problem, that if you do not get it off the ground, you will not be able to reduce the cost. And if you cannot reduce the cost, you cannot get it off the ground, right? You see, this is a difficult problem actually to solve. Okay, so I'm changing the gear. Any other comment, questions, anybody?
Sir, I would like to add another point. So regarding the previous slide,
Yes.
regarding that previous slide, so this RFQ EU aviation proposal, it has
Yeah.
But the EU regulation says by 2041, all the source of carbon should be biodegradable.
Right. Right.
So it's also a challenging aspect in that.
In many countries,
Yeah.
yeah, that is true. Absolutely, I agree. Yeah, that is challenging for many countries. I do know, like again, I have a project on that SAF, and working with some of the companies. I do know that in especially in the US, that's a market I most well aware of. There are a lot of energy crops. These are short rotational crops that basically these plants actually grow in 3 to 5 years. This actually grows like 30-meter tall. And so you then actually utilize them. A lot of research has been done. So basically these are, they know as the energy crops. They rapidly grow, and then they will, you can actually convert them to fuel, and then you go to next rotational crops actually. These are short rotational crops.
In fact, another example like sir, actually Tata Steel did a project approximately 2 years back in Jamshedpur plant. Uh, so since the regulation was not clear at that time, actually the carbon that they are absorbing,
Uh-huh.
initially they planned it to use that CO2 for the production of green methanol.
Uh-huh.
But later on they came to know since the source of the carbon is coal, they will not be getting that green methanol tank.
Right.
So as a result, that project was dropped.
Right. Yeah. Yeah. Makes sense. Yeah. Absolutely. So we'll move on. So in terms of CO2 capture technologies, where do we sit here? If we look into here, we have the absorption, cryogenic, and membrane. All of these technologies over here. And absorption, we have chemical and physical. This is a very important category here as well. Membrane is also a very important category here. And we will be focusing on the absorption here. Many different type of adsorbent are yes. Many different types of adsorbents are being actually considered there. But I just wanted to say that this is one of the many technologies that are being considered there. Hybridizing these technologies makes sense, and I'll be discussing some of those. So what is adsorption? This is just to give you, many of you are not from this background. So I just wanted to say, basically, this can happen for gas, solid, liquid, solid, and those type of systems. For water purification also it is used quite often here. So this, some solute will be sticking to the surface. When we say stick to the surface, that does not really mean the sticking, that basically meaning some kind of a weak bond or a strong bond formation there, which we call the adsorbent, right? And then what we need to do is that we adsorb it from the gas or the liquid, and then we need to desorb it. So it goes by a cycle: adsorption, desorption, adsorption, desorption. When we say the rate of adsorption and desorption become the same, we say the system has reached equilibrium. And this happens due to the surface energetics. And I'll be discussing some of the thermodynamic aspects perhaps day after tomorrow's lecture actually. Okay. So the first thing is that delta G is negative for adsorption. So this is actually spontaneous, right? That's what this thing, something which you need to know here. Adsorption is exothermic, so we know by our convention of sign delta H is negative. You cannot just take it at the face of it. This is one of the biggest thing here, and as you will be discussing here, this delta H actually impacts lot of things. So you can have one of the greatest adsorbents, but if this delta H is very high, energetically it's not favored. Okay, so that is something which you really need to consider here. Now, types of adsorption will depend upon how these molecules interacts with the adsorbent and also among themselves. Okay, so I will discuss this from the perspective of there are three main types: physisorption, chemisorption, and physicochemical adsorption. So physisorption is basically where, if just by the name of it, right, it's a physical adsorptions mainly due to the weak van der Waals force. And then when we have the chemisorption, then it forms a chemical bond, right? And that basically means is that there is one type of a material, like mainly amine type of a material. This is impregnated or immobilized in the solid. So many of you, as you are working in the, like you were talking about metal organic framework, that metal organic framework can capture through physisorption. You can also immobilize some kind of an amine there to have it as a functionalized there. So it can both do chemisorption and physisorption. And we have actually a couple of papers on a metal organic framework which was impregnated with a diamine appended and tetraamine appended metal appended MOF, and it shows very peculiar properties in terms of the isotherm and the nonlinearities, and I will show you some of those results later on, that saying that it can actually lead to a very, very complex mechanism that is difficult to capture through modeling. But it can be, both of them can take place together. So these are not exclusive. So the confusion always comes like, okay, so physicochemically is where both of them are taking place. Like I was saying, metal organic framework, when functionalized, will do both of them, okay? Now, if we consider both of them, what are the differences? So if you look into the bond, like physisorption, is these are weak and the long range form that forms here. Chemisorptions are strong and the short range bond that gets from here. Look into this number here. This enthalpy is 5 to 50. Most cases, this will be like 10 to 15 or 20 kilojoule per mole. This guy can be very high actually. Like generally, as you know, like if you have an monoethanol amine, it will have about 95, 90 to 100, mostly take about 95, give or take plus minus 5 kilojoule per mole is the heat of absorption in the solvent. If you immobilize it, this heat of absorption becomes very complex. It's very difficult to say what that value should be, right, predicting it. But these are generally high. So like those diamine and tetraamine appended MOF that I was saying, this has got a value of 65 to 90 kilojoule over mole. So you will be seeing that I will be discussing these very often. This is a take-home message for you. This is a number that you need to look into, this heat of absorption, why this is good and this is bad, right? So this thing actually hurts you in both ways. So when you are doing in absorption, this heat will get released and it will heat up. If you heat up from an equilibrium perspective, then if you look into the adsorption isotherm, your equilibrium will go down. So you cannot capture as much. And then when you are trying to desorb, you will need this much of energy to provide to get it off. So it hurts you both ways. Unfortunately, some of the excellent adsorbents, which actually has got really nice adsorption isotherm, very high loading and all of that, has got chemisorption properties. And that's how they become very specific. But they have got both sides you need to weigh to find out what you should really go for. The other thing is the selectivity. This can be low selectivity and and this could be pretty high actually. So it could be very selective because of the chemisorption. And that is why you know the monoethanol amine, diethanol amine, all of those amines are still so favorite. Energetically they are not good, but the thing is they are so specific. They will only capture certain components there. So that's why even with those energetics, people love it. I will discuss what is the problem that if it captures something else. Now, sensitivity of adsorption to pressure, this is also another thing that you need to consider, especially if you are thinking about a membrane, especially if you are looking into the steel plant capture. Those which has got a very high CO2, you can take advantage of that high partial pressure of CO2, but this really helps the physisorption. Chemisorption can be largely insensitive. Monoethanol amine can capture 99.99% CO2, no problem. It will capture. These are so much like it because captures is through chemical reaction. But for physisorption, you cannot capture it. So that is also important thing here. Sensitivity of adsorption to temperature, this will decrease. And I know Dr. Pala will be discussing this adsorption isotherm, and you will see how those things behave. You will see that this will actually keep decreasing. Chemisorption, very complex, very, very complex, because there is one chemical part, one physical part. Physical part is hearts, but chemical part is very difficult to say actually. It goes both ways actually. Now, one question comes is that if you're in the market and you are a business and you say, yeah, I'm actually evaluating like 5 vendors, or I'm trying to develop 5 technologies, which one is the best? There is not one good answer. You have to analyze it. So what are the things you need to look into? First thing is that it depends on the partial pressure of CO2 at the inlet of the capture unit. This is very different when you are thinking about post-combustion capture from a coal plant, 10 to 11% CO2 partial pressure. You are thinking about natural gas combined cycle, 4 to 5%, versus you are thinking about the cement plant, versus you are thinking about the steel plant, the blast furnace gases. Everywhere the partial pressure of CO2 is different. So this is the suitable technology depends on your partial pressure of CO2, one of the criteria. Other criteria is what is the percentage capture you are desiring. If you say, I want to capture 90% from a blast furnace, versus you say, I want to do 99% from a natural gas combined cycle plant, it's a completely different ballgame. Your partial pressure of CO2 is really nothing. It's like 0.0001 bar for the natural gas combined cycle case. So there you need a completely different technology. That's why the hybridizing the technology can actually help, like membrane with sorbent or solvent with a sorbent, and those type of things can do actually a lot of good work there. The other thing is what are you going to do with that captured CO2? If you're saying that this CO2 I'm going to putting it underground, it's a different requirement. If you say this CO2 I want to use for enhanced oil recovery, it has a different requirements, because like for example, there is a strict oxygen requirement if you are putting it for enhanced oil recovery, because you have this oxygen going there and it can create explosive mixture there. So you are not allowed to do that. But if you're putting it for geological sequestration, it is okay to do that. Then other thing is, like I do know that at Iceland and Microsoft bought that direct air capture, that green tag actually for that Iceland based CO2 capture unit, that is being used in a nearby Coca-Cola plant for the CO2. That's a direct air capture. You capture from air, and then they use their geological energy for regeneration and all of that, and then put it to a Coca-Cola bottling plant nearby, right? That's a completely different CO2 requirement, because it's a food grade CO2 requirement. It's a 99.999% purity of CO2. So you have to understand where I'm trying to going to utilize it, or I'm trying to produce formic acid, I'm producing methanol or whatever. So that is another important thing. And also what contaminants you have in the incoming gas. Like blast furnace gas has got all kind of things there present here. Coal gas has got all kind of things here. Natural gas combined cycle, very nice, like in terms of contaminant, not so much. So all those contaminants, you must take those into consideration. Yeah, this I kind of already mentioned that for this. Like for example, if you're thinking about NGCC plant, and if you're doing 90% capture, partial pressure at the outlet is 0.00 bar, and then from 99 point capture, it enters the direct air capture range, right? If you compare it for the PC plant, with 90% capture, it is 0.01 bar. So see the comparison over here. And beyond like 99.6% capture, then we'll capture the DAC range, right? That is what it is. Compare this to the cement clean off gas, which has got about 30% CO2. It's very different ball game actually. So the sorbent technologies will be very different. So it's not easy to give you one answer for this one. Okay, the other thing is why we care so much for that sorbent. So the point you will be, and over the next 5 days we will be discussing this, but the equilibrium and kinetic properties of these sorbents greatly differ at this PCO2, low PCO2. Some of the sorbents are pretty forgiving for low partial pressure of CO2. These will still go to a very high loading. Some of them are highly sensitive. So you have to think that one. Other aspect is the kinetics. That is one more important thing. Equilibrium tells you one side of the story, but kinetic gives you the true picture, how much of close to the equilibrium can in reality you can capture. So if you're doing it in a lab scale and you say my equilibrium loading is so much, in reality you may not even be able to capture 10%, go close to the 10% because of the kinetic limitation. You do not have the eternity just like what we do in the lab. Like in a lab, you can wait for 5 days, and a graduate student running a lab, no, not hurting the graduate students, but saying that they figure out what is the equilibrium, you wait for 5 days and say, this is the best data I could find, right? You are happy about it. But reality is that in an actual capture plan, this gas will be there for a couple of seconds. What is the close to the equilibrium you can go to? Because we are talking about a massive amount of CO2 flowing through the system. Your residence time is very low. If you say, I want a 5 days of residence time, the Jordan bed will be the length of India actually, right? So it's not acceptable. So that's the other part you must take into consideration. The other thing is that if you have only consider physisorption, and if you want to go for a high CO2 capture percentage and you have a low concentration, it can be very difficult to go do that by physisorption. This can be advantageous for chemisorption because they are largely insensitive to partial pressure of CO2, but the point is about the energetics. So as I mentioned there and discussed, this chemisorption has got a very high heat, so it hurts you both ways. So you see, there is not a one solution here. Like this is nature, right? There is no, we always say there is no free lunch theorem, right? Like there is no free lunch. You get one advantage, there is a disadvantage. So you have to weigh the advantages and the disadvantages. This is one of the thing there, that physisorption helps because of the low energetics, but you cannot achieve those high capture percentages. And chemisorption is the other way around, okay? Now, other aspects you have to remember is that when you think about the chemisorption, you can lose the chemical that is immobilized there. This can happen over time. So they could have a stricter operating conditions. Like you might say, temperature must be below 110 degrees centigrade or whatever, or the moisture content should be below some values there. These constraints may or may not exist for the physisorption. So this is other aspect you have to take into consideration. Constraint with respect to the operating condition. Another thing is the contaminants that are present, what happens. You might actually think about, why do I care if I have a contaminant present and I co-capture with CO2? So I can co-capture nitrogen and CO2 together. What is the problem? And I can put it under the ground. But what you have to remember there is that that nitrogen that you captured, you are compressing that nitrogen also along with CO2. So under what conditions CO2 is stored, if you're trying to think about storing there? It's more than 150 bar. It's stored under supercritical condition. That's where it is stable conditions. You put it through the pipeline more than 150 bar. So you're taking that extra nitrogen that you capture, like 5% nitrogen, put it through this, and then 150 bar you are compressing. That will actually take your energetics very go down, because nobody will give you credit for that much of nitrogen, and it's there. There are other things like sulfur is one of the nastiest stuff, because they will do the corrosion of the pipelines. Moisture content, they are also very bad, because when you go for the supercritical condition, that moisture will form hydrates. And that's one of the other aspects that we have to take into consideration. So contaminants is one of the big issues that you need to consider there. Other thing is the absorbents undergoing chemisorption and generally costlier than undergoing physisorption. And the other aspect that which you may not or should not forget, and this is something which I learned, to be honest with you, by interacting with the industry, is scaling up. So I can produce a absorbent in the lab scale. I am a chemist, I am doing it, I just produce a couple of grams. If somebody comes to me and say, you know what, for CO2 capture requirement in India, I need million tons of this material. Can I produce? Maybe I do not have that much of material on earth, the raw material that I need there. That's other aspect that which you have to remember here is that scaling up the solvent of the absorbent to the scale that we need can be challenging. Okay. Um, so capital expense and commercial feasibility, and that is where the governments can come in. So capital expense, because all these materials, if you're thinking about the solid absorbent, you are purchasing it, so it's a one-time purchase. If it is lasting for 5 years, you are done for 5 years. Who pays for the money? If the government comes and say, well, I will pay 50% of the money that you have, or I'll give you a tax break and all of that, it becomes economics becomes completely different. So this part is something which you need to consider, and then combining everything, an economic analysis is essential, and you must do it by considering the uncertainty, consider different scenarios. So as I said, for any selection, it's very difficult to analyze it without going all the way up to the economics, because there is no clear winner for these technologies. That is why we are developing all technologies. Can you come up with a technology that is very selective, operate at low partial pressure at CO2, but has got very low heat of adsorption? It's a challenge for you, all the researchers in the world. If you can do that, you will be a billionaire. Nobody has the technology. That's where all the challenges are there. Unfortunately, there isn't nothing that we could come up with so far. So that's a challenge for our future researchers. Hope somebody will come up with something in one of those days, okay? So I'm not sure where we are doing at the time. I think maybe at the lunch time, right? Already coming. 12:45. We're supposed to end at 12:30, right? This one, or? Okay. I'm mostly done, actually. I just basically wanted to say, take about 5 to 10 minutes. Concluding remarks are that we need considerably high effort all over the world for decarbonization. And CO2 capture is one out of many options. But remember, this is critical for many countries. Many countries, like I know in the United States, one of the big advantages that they had was the availability of the shale gas. So natural gas, because that itself dropped the CO2 emission considerably. And then, of course, they don't have solar like us. Only some states have the solar. So India, for me, it seems like the solar is the great option. But the problem with the solar is massive capital expense there. So that's where the problem that comes there. So if we continue to use coal, then the CO2 capture is one of the critical things that is important there, because we cannot get rid of the carbonaceous fuel such as coal for a while. Adsorption is a very valuable technology from varieties of sources. Another advantage of the adsorption is that you can just almost put them anywhere. Like that's why a lot of these direct air capture technologies, people are considering adsorption, because you can put it in the middle of the city, actually. I do know there was also a project, it's probably Netherlands or Norway, actually. They had the projects like installing it on all cars that drive around the city. So had almost like a canisters, it's a solid absorbent. So it just put it in all cars. So as you are driving there, so it captures CO2 from the ambient and also emissions from your car exhaust, right? It captures there, and then at one point you open up the canister and put it at a place which collects everything and dissolve at some other location. So that was a very nice concept, that you could do this capture and they do the regeneration at one place, but capture in a distributed manner. So that also can happen. As I said, that you must select it very carefully by considering number of factors. And this was my view. I will say that in my view, economics is the final thing, which gives you everything. If you can say, this will cost me so much of INR, that clicks with everybody. Like if you go to a political person, you go to a go to somebody in the community and say, first question come, how much money we need to do this? This is the first question without understanding all the technical aspects here, okay? So questions and any other thoughts anybody has. So first I'll check any questions anybody has, any clarity, any questions for the adoption. Yeah, speak up. Don't be afraid. Like we'll be here for next 5 days. Speak up, and we'll answer questions. Yes.
So one question, sir. So regarding the commercial aspect and how energy intensive it is, as per my understanding, so absorption and deabsorption means when it is releasing the CO2 for utilization, deabsorption would require much more energy than whatever the energy it has been utilized for the means absorption process. So on that basis, sir, one though not related to this one. So as you mentioning that we need to find out the solution, what is the best cost-effective way. I'm trying to understand from you, sir, what is the prospect of carbonic anhydrase using those kind of catalyst and so for this direct air capture or from the point source? So I'm just trying to understand from your point of view.
Yeah, this is a different aspect also. Thanks for bringing that angle. There are a lot of actually all the catalyst as well as that could be producing some chemicals. Those could be considered there. So in those cases, you do not need the desorption energy because you are not releasing the CO2 at all. The point here is what you have to keep in mind that if you can come up with a clever chemical that has that kind level of market demand and utilization, then yes, of course. So in that case, you adsorb, you do not have to desorb there, and you can save money there from this perspective. Problem is that most of the chemical that people have been thinking about, including also a lot of putting it in the cement and building it and putting it in the building materials and all of those, lot of thoughts are there. But yes, so it is possible, but there is not a single product that has got that much of a demand that can take that much of CO2. But it will be, we need many solutions. That's the thing. So there is a market for lot of options. So there is not a single solution to this problem. So of course, we should explore those utilization approaches that does not require you to dissolve. There is also a lot of discussions in terms of what we call the reactive CO2 capture. We'll not be discussing it here much. The reactive CO2 capture basically means is that you are capturing CO2 from within the source where it is getting produced and producing a value-added chemical right there. So it does basically means is that you do not need to capture the CO2 separately, but at the source where it is being produced there. So those thoughts are also there. Okay, other questions, comments, discussions? We are ready for lunch? Okay, anybody online, do you have any questions? I hope we can see the, should I go for stop and see if anybody has anything on chat? Yes. Okay, yeah. Dr. Sridhar already said if you have any question, post it. Yeah, anybody online, please let us know if you have any question. Already? Okay. Thanks, everybody.